Hi, everyone. I'm happy to present our ECCV-2024 work, Equivariant SE3 graph network model for sparse point cloud registration. This work was done in collaboration with Jiankang, Zhuoliang Luan, Claude Kosham, and Bing Wang. Our motivation is that traditional C and transformer-based models for point cloud registration have several limitations. The figure below illustrates a standard pipeline for point cloud registration. They require accurate correspondence supervision during training. They are not robust to high outlier to inlier ratios and suffer from high computation demands. They also overlook underlying geometric topology of data and often require extensive rotation augmentation to handle SE3 transformations. Graph neural networks can capture the geometric topology of point clouds by modeling relationships between key point features and the graph structure. This allows them to handle sparse point clouds effectively. However, traditional GNNs do not explicitly learn SE3 equivariant features, which limits their ability to handle point cloud registration robustly. So we introduce our model as shown in the figure, which first creates SE3 equivariant graphs for both source and target point cloud scans. Next, we compute the similarity score matrix to find correspondences between two frames. Finally, we use the correspondences to predict the transformations to align two point cloud scans. Equivariance refers to the property where if the input undergoes SE3 transformations, the model's output changes in a predictable way. By ensuring that features remain equivariant after passing through the model, we can achieve more reliable feature representations. This leads to better correspondence matching and more accurate transformation predictions. This figure shows TSNE visualization comparing output feature distributions of different models. In the first row, we have the original inputs and the output TSNE features of three models, GCN, SpinNet, and our model. The second row shows rotating inputs and corresponding output TSNE features. Our model exhibits SE3 equivariance. In Formula 1, traditional GNNs start by calculating edge features MIG from hidden features of the connecting nodes. Then these edge message features are aggregated to update the node feature H at layer L. This process effectively models the relationships between nodes but lacks SE3 equivariance. In Formula 2, we extend the traditional GNNs by introducing SE3 equivariant message passing in MIK. We update the node coordinate embedding X by considering relative position of neighbor nodes. The projected message MIK is mapped into an SE3 equivariant feature, then concatenated with node feature HI, finally to be integrated into node feature of the next layer through MLP. In Formula 3, to maintain SE3 equivariance, we construct a local coordinate frame FIK for each node based on the relative position of the neighbor nodes. These frames allow us to project edge features in a way that preserves equivariance properties. Another key component of our model is low-rank feature transformation. This technique improves computation efficiency by aggregating feature descriptors before similarity matching. The right figure illustrates LRFT of our model. In figure A, LRFT reduces the feature number by applying two linear transformation layers A and B with low-rank constraint R. In figure B, the zoom-in submatrix shows the similarity score matrix after LRFT. Now, let's look at the overall architecture of our model. Our model architecture consists of three main components: an encoder, a feature match block, and decoder. First, pointwise feature descriptor are extracted from the source and target sparse point clouds and pass through SE3 equivariant graph layers. Then, using LRFT, we compress the stacked feature matrices and compute the similarity, and leaving the decoder processes through pooling and folding connect layer to predict the relative pose. Here we present the results on the 3D match indoor dataset. Here are the more results on the outdoor KITTI dataset. Here we compare the performance of our model with and without SE3 equivariant features in graph layers. There is clear feature matching improvements when equivariant features